changing the
This
size of the
conference will now
connector,
be recorded.
but that would be highly dependent on what the allowable performance parameters are in fluid versus the air. And
So you are concerned about the
arc,
possible arcs that can happen in
ARC,
there?
yep, arc, yep.
Yeah, sorry. Yeah.
No, that's okay.
That's of course depending, as you say, of the fluid properties, right? So
Yes.
yeah, I understand. Okay, so that's something I will also note for them. There is another work stream which is about fluids and material compatibility as well, and I think that's a question that we might get an answer from there.
I think that's an interesting point, and from a safety perspective, I think that's really the key. Does UL define the different? I mean, do the separations depend on different materials or a dielectric measure? I think that needs to be clearly defined, right? Is it distances, and how does it? Yeah, fluid. I think you perfectly captured that, Oreo. This is a very good question.
Yeah, indeed.
Yeah.
Actually, this is something that we have not considered before. It's something we have not. Yeah, so this
And
is
anybody
very
in
nice.
power, I mean, anybody who's doing any power stuff, I think this needs to be defined, just like we defined that in creepage and clearances in the other
Exactly.
instances. Yep.
Yep.
So, Dennis, you will be speaking of minimum or maximum arc distances.
It's typically we design around minimum, right? So we're trying to get the metal parts as close together as possible without having a safety risk.
Okay. Thank you. Thank you for that very valuable information.
Yeah, I would reword that though. Metal parts as close as possible without risk, right?
Yeah, there shouldn't
That's
be
all.
risk at
Sorry.
all. Yeah. Okay. Any other inputs in regards with safety and equipment related for power distribution immersion? Anybody has something that would like to comment to add? Okay. Generally, we are always thinking on the single phase immersion because it's maybe the one which is having an easy access when it's operating. But of course, in the two-phase immersion, there is higher temperatures and maybe other things that we need to also think in the future, just to avoid any human harm when the tank is in full operation. So I will also note down here temperatures. We consider while in operation. Maybe this for the next day. We'll have somebody from Fluid. I think the other day we had somebody from Shell or Castrol, if I recall. Okay, if nobody has any other feedback, I will jump to the next topic we had for discussion the other day, which was about the busbars, but more speaking about the material compatibility, temperatures, density, safety. Well, safety was already spoken in the other one, and the current limitations. Just to give a brief introduction, and speaking about the density mainly, the materials we are seeking for and the amount of materials we are guessing that will be required to define the requirements for the ORV3 might be, of course, bigger than what it was already working for ORV2. So this is, of course, open questions about what are your guessings, what are your limitations thinking. Maybe the bus bars need to have a specific cooling because we will be reaching higher temperatures while high power distribution. Is this something that you are aware? Open questions. Dennis, I don't know if you were speaking about busbars. I don't know if you have also some information thinking about that.
Sure. So again, you have two different, I see two different avenues here. One is can an existing part that's designed for air work in the solution? And from a power perspective, usually it's advantageous to use it in the fluid because the thermal properties are so much better, so it performs at a lower delta T, for example. Um, and so in theory, you could put more current into it. The flip side of that equation is we have an opportunity to design connectors at the same current level, but with less material. So we could make them with less copper. We could make them, because it's thermally more efficient, we don't need as much material to conduct the same amount of current. And so then you end up with connectors that are optimized for the application. That's what's going to happen over time as market adoption moves forward, right? Um, so understanding what those new limitations are will be, uh, and what we can design around, will be where uh, these challenges come about, I guess.
Okay. Because at the moment where personally in my case, I've been in some data centers and I've seen that to communicate sometimes between corridors, there is big bus bars which are just communicating with some electricity, but they were never cooled down. They are just not having any more than the cooling of the room. So do you guess that at some point we should cool down specifically in immersion the bus bars maybe, or they will be just fine?
Well, in this application, you have the bus bar is immersed in the fluid. The way I understand it, it's lying horizontal in the tank, right?
Yes.
There's a lot of different solutions in the marketplace right now, and the what we're talking about in this group right at the moment is one of the solutions, which is a tank-based, all the servers, and so then the power is of the rack is also in the tank, right? Because it has to get to all the servers. There's other applications where all of that bus bar equipment would be external to the tank, so to speak, or the immersion fluid, and those would be your normal air solutions. So I
Okay.
don't see them doing immersion for rack to rack power.
Okay. So do you think that the adaptation, as you were commenting before, that maybe the air bus bars nowadays need for immersion are not that different, actually?
That's hard to say. I actually think they're pretty substantially different, but I don't know what that evolves to. I don't know what that looks like from a rack. Let's say inside the rack, what if you were to optimize the bus bar system for an immersion environment, you might end up with a very different uh, design.
Okay. Very good.
I have a question there. You bring up a good point, which is if you've got a lot of racks in a row and they're all laying horizontally, how are you feeding power into those fluid enclosures in a linear line? Are you using an overhead busway like a star line, or are you using something mounted directly behind those enclosures? What's the thought process and the topology for getting power at least to that enclosure?
So Mark, you're talking about the AC power going into the power shelf connectors.
Whether it's AC or DC, whether you're generating renewable DC off of a PV array external, or whether you're bringing AC into the facility and going to rectify it on a power shelf inside the enclosure.
So I think that may be something that individual manufacturers have an ability there, maybe to differentiate that AC if it is AC power. Well, let's just assume it's AC power for right now, okay? I think the different manufacturers can probably bring some features and differentiation on that side of it that honors the intent of the OCP that, hey, these power shelves are swappable from, vendor B, C, D, that they interoperate, but how they manage the AC cables and all that plugging into the power shelves might be something that we leave for some differentiation rather than speccing that out to the final detail.
Correct. And actually one of the, let's say, interesting or attractive points from the OCP versus 19-inch traditional servers that the industry is looking at is that we are more clean when we speak of the cable management, right? So in an immersion tank, by the start, you're already avoiding to have power cables from the servers because they are having the power down from the power shelf and the bus bars. So that's something that you can already reduce. And also typically there is not screws. You're trying to place the things and make them fit, but without the screws. So with all of that and with the bus bars in place, you're having a clean environment with less cable management, which of course in immersion is more difficult to manage rather than in air. So here on the power shelf management, typically, yes, there is the cable which is feeding the power to the power shelf, and then the power shelf is distributing all of it under with the bus bars. And that's the end-to-end as you were asking.
All right, thank you.
No problem. Of course, what John was commenting will be the ideal thing, that we are reaching a point where there is not that independent or individual developments, and we can all have power shelves which are swappable, and it doesn't matter if this is coming from the vendor 1, 2, or 3. All of them are compatible, all of them can work with the same specifications for immersion, and all of them are compatible with different type of bus bars.
I have maybe a somewhat naive question based on the way that you're describing that. You're talking about using the OCP defined power shelf by various vendors that interfaces with the 7-pin AC input cable. And that cable, I'm curious about the installation. Does this power shelf reside also in the fluid? And so you have to mate the cables first and then lower the thing down and hope that you're not torquing on the cables. I've just not seen an implementation of this. And so how the power gets into the tank has been an open question for me as well.
Okay, so in my case, I will be there. I don't know if you guys will be joining the OCP Summit in San Jose, and we will be over there. There is some cases that you can see real time working. But basically, the thing is that the power shelf is getting the power usually from the top. So this is making it get this power through the cable. One of the principal problems that the industrial immersion is suffering is about this capillarity thing we were commenting. So at the moment is something we need to tackle, because usually the fluid, any fluid that is dielectric and there is an electricity conductivity inside the fluid will make that that fluid will go up through the cables and out of any tank, any recipient. So that's something that we should address. Yes, typically there is the bus bars horizontally in the bottom of the tanks. There is the fluid. There is a power shelf full of PCUs, of power supply units, and then you have a cable coming from the top, which is giving the power to that power shelf, and the power shelf is distributing down through the bus bars. That's the basic concept. If you have a more concrete question, maybe we can tackle it.
Okay, I look forward to seeing your demo at the show.
Yeah, no problem for that. Okay. I think that we have been speaking about all of this. I don't know about limitations. I don't know if anybody of you have some ideas about the market expectations, about current limitations. Of course, the density, as it increases, it's an interest for everybody, but of course there is limitations, like speaking of bus bars, we cannot today, I guess, with the current technology, develop a bus bar of 500 kilowatts. So I don't know if the guys from Molex that you were speaking now here, and you have some previous experience of that there is any limitations that you can see as a stopper for the next 5-10 years on the industry.
Yeah, I wouldn't have any
One,
comments on that yet.
yeah, I guess I'll just add kind of one area of focus that we've been looking at that I'm not sure whether it's relevant to the group here, but on similar with these dielectric constant performance with regards to signal integrity. After a certain frequency, the dielectric constant is so different that it affects the impedance of the system. And so there's kind of this trade off between systems that are operating at a particular data rate today being able to be dumped in the tank and showing the thermal benefits, but then the actual systems that require this solution for um, immersion cooling that would be operating at a higher data rate, which are impacted by that dielectric constant and those signal integrity properties. So I think there's a challenge about, as Dennis mentioned, purpose-built connectors versus using existing connectors dipped in the fluid for those higher data rates, and will it perform as expected from a signal integrity perspective? So there's a lot more investigation that needs to be done in that particular area, and I think that's one thing that could hinder widespread adoption, assuming even if we solve the power distribution
Yeah,
question.
there is a fair amount of work already underway there on signal integrity, and our friends at Intel have submitted a proposal for some fluid specifications that get into some of those properties in terms of loss tangent, DDFs, et cetera, et cetera. But certainly within the scope of this project, we're worried about the DC power and not the signal integrity. So we're at DC with what we're doing with here. So it is definitely an interesting and important conversation, but I think it's not really too relevant to the ORV power architecture that's going into the racks necessarily.
Fair enough.
Yeah, I mean, the question was more, of course, all of these items you mentioned are in relation to define this strategy in the future. We were just wondering if you have other input from other market, from other interest people, which is just willing to reach an immediate objective of kilowatts. If not, there is just an open question that will continue to be defined between everybody, I guess. Maybe the
Sure.
density is not, maybe density is
The
not the
the
only
other
objective in the future.
Yep, the other open question that we have is related to mean time between failure or reliability.
Correct.
So, and specifically related to some of the failure modes that may be associated with the two-phase fluids. So, this is all hypothetical right now. We're still just getting into the research on this, but if you have a contact interface that's generating heat, right, because of the high power that's coming through here,
Mhm.
um, in a two-phase fluid, if that's a localized hotspot, you might get a two-phase fluid conversion at that point, right, at the contact interface. So literally the fluid's boiling right at the point of contact, and um, because of the heat that's generated there. So does that deposit contaminants at the contact interface, or the contaminants that are in the fluid, and how does that relate to the failure modes? And then ultimately, the only reason that's important is because understanding the reliability of the product over years. And that is an open question that we have, that you were asking about limitations. We're still unsure about how that will work in a two-phase environment.
Yeah, do we have any two-phase folks on the line? You bring up an interesting point. I think the two-phase guys have added some fairly good filtration to their system to pick up the contaminants so that what's available to be, left behind after the boiling is fairly minor, and they've learned from that and have made some changes to their offer. But is there anybody two-phase on this call?
And that's, yes, John, I think that that's correct with the caveat that then it's up to the user to swap those filters, and how often does that occur, and those obviously would then apply directly to our connector reliability.
Sure, sure, absolutely. Yep, agree with all that. Yeah, and maybe it's a fluid monitoring activity as well. You know.
We had the other day Barath from Microsoft, which was sharing a very interesting presentation about the two version, two phase immersion, sorry, about some limitations, some advantages. So I don't know if I will be able to ask him to join also here so we can share some inputs, or maybe the Gigabyte guys who have also a lot of experience about that. But yes, it's actually a really nice input to have. Okay, let's gonna jump to the next topic if nobody has anything else to say. We had the challenges of air implementation versus immersion implementation. This is a very, I will say, hard topic because I don't know if anyone has experience to compare the MTBF, as we were commenting now, the mean time between failures, and some other inputs that can help help us inside. We are in the immersion part inside OCP to share the benefits and to show to the community that the immersion is the same important and as the air implementation in the OCP community. And I don't know if somebody has inputs of MTBF, of easiness of installation, of some other inputs that might start conversations and questions. If you want, I can start myself, which well, for the ones that you don't know, I'm the OCP work team leader to add here with Harry, but personally I'm working for Summer. So for example, the experience that we can bring up or share is related to the tanks, to the racks. So for example, the challenges of air implementation versus immersion implementation, speaking on racks, for immersion will be well, for example, one of the bigger stoppers will be the compatibility of all the IT hardware that needs to run inside the fluid, comparing to what it is just an easy rack air installation. Speaking about power, I think it's also related to the cable management. The cable management, because of the cable compatibilities, materials, and the capillarity, and the way to make them all look nice, same as there is a perfect design and layout for the air is not that easy in immersion, so that could be a challenge. So, for example, I will start myself saying that rack installation for immersion is way more challenging because of cable layout, popularity, and cable compatibility. There is,
When
for
you say
example, yeah,
when you
sorry, go
say
on.
capillarity, are you referring to the fluid migrating up the internal jacket of a cable? Is that what you're referring to?
Correct, yeah. So the fluid is typically going out of the cable when there is power or copper cables. So there is a problem that there is also some other companies that maybe will be joining on the next calls that were also invited. I guess that the next step here is to somehow develop the connectors that some of them are already existing, which are breaking that capillarity, but also
Mhm.
there is some cables which might be sealed inside. So at the point that the fluid is going up through the cable, it cannot go further because the cable is sealed inside, because the capillarity is happening inside the cable, not outside of it.
Okay, I wasn't sure of the term. Thank you.
Sure, no problem. And sorry, one more in case of immersion would be, for example, the needs of very strong technical floor, so it can hold all the weight of a rack full of fluid and servers, which is typically more heavy than a rack. This is, of course, not very related to power distribution. Still, though, I think related with cable management. I don't know if anybody has more inputs about these challenges.
Well, we need not exaggerate the floor loading because of immersion. We need to keep in mind that the racks now are horizontally oriented, and therefore the footprint of the floor on the rack is considerably greater. Good news is that power capability of the rack also went up, so you do end up with a higher power density capability, but you are spreading that load out. A lot of analysis, depending on the IT load, you end up with very similar loadings per square meter between an immersion rack laying on its back versus a vertical air cooled rack sitting on a fairly small footprint. So just kind of just generalization there, high level. But I don't believe, unless somebody has some other data points, that the fact that we're going to a DC power distribution with power shelves and ORV3 type power architecture, I don't think that that's going to add any significant weight in of itself to a rack that we'd be taking power supplies out of all the servers and putting them more centralized within the rack itself.
You're completely right, John. Yeah, I think this is not,
S-
yeah, the
So,
power distribution will change.
John, one question on that. What about the other solutions that are like where they're doing the immersion that's self-contained in the server in the individual servers, and that's on a vertical rack? But then each server has, its own little fluid tank, um, or other solutions. Are we really just focused on ORV3 solution here, and that's that? Do you know what I'm asking?
Yeah, no, I
How?
do. It's a great question, Dennis. And then again, the other point is that depending on the dielectric fluid, we have fluids that have fairly low specific gravities, less than water, and then there are fluids out there that are quite heavy compared to it. So that's an important thing to keep in mind, that not all fluids are equal in terms of their density and therefore the floor loading. I, and I don't know what we think about. I was of the assumption that probably the vertical chassis by chassis level immersion cooling probably wouldn't be in this scope initially, but that doesn't make that being the right assumption. I was just assuming that we're probably talking about more what we all accept as conventional horizontal tank slash racks that get multiple servers into the same reservoir of fluid. But it's a good question. I don't know the answer to that.
Okay. And then follow on to that, of course, is are we considering both single phase and two phase solutions, because the cable routing, for example, is significantly different, because in a two phase solution the tank has to be, sealed,
Absolutely.
right? And
Yeah.
so that presents a different set of challenges than the single phase tanks.
Correct.
No, it surely
Although,
does.
yeah, I'm not sure what and again, I think goes outside the scope of this. This is why this is so challenging. But what single phase fluid? What does it evaporate, and where does it go when it does that? Um, and things like that. If you're not in a sealed environment, I've seen a couple of calls on that, but it's kind of glossed over those concerns.
Yeah, most single phase fluids have very, 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 very low volatility content. And so what you lose out of a single phase fluid to the atmosphere is trivially minor. Okay.
Okay.
As a and two phase, of course, by design, are volatile on purpose because the intention is that they do boil at higher at the higher heat flux items to cool them. So, I mean, it is a good point, and it may be that we leverage some other work and give guidance like, hey, if it is two phase, consider cable glands or whatever as you exit the rack to sustain no more than such a percentage mass loss over a year through those features. I think it's a good point. And then I think there was a discussion about capillary action of the cables, depending on how you manage it. Some people could maybe be creative and come up with ways to mitigate that, where some people may be careless and contribute to that. So there may be some statement in there as well as far as fluid loss through capillary action for single phase up through the cabling, and mass loss through the glands that maybe would pass through the rack for two phase. So that may be something that we want to give some guidance to, or we may want to say, hey, no, let's maybe talk to the immersion requirements and let that be more generic. I don't know. It's a good point. I don't know if we throw that in the scope here or we get somebody else to handle that in their scope. But really great questions for sure.
Yeah. Indeed. Actually, on the material compatibility group, there is a lot of conversations which we will try to get some feedback, and let's see if we can have them talk together. As you were commenting very well, John, the single phase immersion, it's having almost no evaporation, and that's even at high temperatures, and I think will continue like that. So, and of course, the true immersion needs to be sealed. So that's two different, very different ways of running the IT hardware inside, and it will be having really two different requirements at the time of looking at this. So maybe at some point we need to make a big division inside power distribution when we speak about single phase or two phase, because everything will be very different at some point. Okay, I don't know if you guys have any other inputs about the challenges, any that you want to add here for discussion during the next sessions. Okay, I'm gonna jump to the next slide. This was a topic about retrocompatibility between the WAR-v2, v3. I don't know if this is something that we are ready to jump in for the past experience that we all have here. I think it can be get open for the next session, but this is something that on the discussions we're having is very important. So if there is something that is already working, well designed and effective for the ORV2 that can keep working for the ORV3, even the ORV3 is having new requirements for safety or density or compatibility. This is something that we should list here, that we are comfortable with. I don't know if anybody has some input. If not, we can jump to the next one. Okay, I will leave it for the next time. This is questions I've got through the email for the group. Maybe the people actually is not here today. Maybe they could not join. So it's just the part of the questions that I brought up for this. For example, the capillarity problems. I think. Sorry for my.
So sorry. You want to go back a little bit, Oriol, on the previous slide when you said yeah, sure, retro compatibility of ORV2 and ORV3, right?
Mm-hmm.
So the one, as most of us know, the key difference is ORV2 is a 12-volt system versus ORV3 is a 48-volt system, right? So ideally, they are for different applications, right? And so this is one thing key. And if you look at the power density, if you look at the ORV2, it fits in 3 OU space, and there are 3 PSUs, and each one is 3.3 kilowatts. So the maximum is like 9 kilowatts. And if you're looking at a comparable ORV3 system in 1 OU, you get up to 18 kilowatts of power. So, it's much, there's a lot more density to it.
Yeah. But Harry, for the ORV2, what you just commented is a close requirement. I mean, it can just be like that, or there is other power providers that can still develop maybe power shelves or PCUs compatible with ORV2, but that are not. deciding?
They can, because ORV2 is in a public domain, and the specifications are in OCP. So it is definitely it has the same thing as ORV2. It's in public domain. Yeah, all the specifications are in public domain.
So as same as the voltage is something that is mainly very difficult to change. The
Exactly.
size of the power shelf, or how many PCUs it will have inside, or how many kilowatts per PCU, that's something that is open, that can change eventually.
Yep. Yep.
Okay.
But my only point here is, Oriol, and with everybody with increase in power and all the pressure to go to high power densities, I don't know how much 12 volt has legs going forward. And I would love to hear from other people, but almost all of us are moving towards 48 volts.
Yeah,
Yes, correct.
given,
And sorry, go on, John.
no, I was just going to add on that, given the big value proposition of immersion is being able to support higher densities, I think it couples very, very well with 48 volt to be able to power the higher densities, whereas 12 volts, maybe you end up power constrained compared to what you could thermally do with immersion, So I think the 48 volt kind of fits within the immersion benefit and value proposition better than a 12 volt might.
Yeah, actually, and also I got before some feedback from the server manufacturers, which were saying that as higher voltage, less conductivity for them, something like that. So I think that's also very good. So we are all focusing on that, and that will be one of the main differences of V2 and V3 because of the density, as you say. So far, we don't know what of the parts and of the requirements used for the ORA V2 might be valid to be used for the OR3. Maybe the connectors are different, maybe the voltage is different, maybe the bus bars will be different. If there is anything which will not be different, it's good that we can tackle it. So we are not doing a new development for that. Okay, there is 1 minute left. There is, of course, some more slides and open topics, but I think we'll need to have time on the next session for that. I will share all this feedback on the meeting minutes, as I'm always doing, and I will publish it on the link that I'm having for this call. And you can find me or Harry, the leader and co-leaders for this power distribution immersion call, in our OCP project mail. So if during this next month there is any questions, suggestions, or topics that you would like to have for debate, please mail us. We can include them here and have an open discussion. For the others, I hope I will see you there in the OCP Summit in San Jose in October. So that will be all. Have a nice day and hope to see you soon.
Thank you.
No,
Thank
thank
you.
you, Oriol. Thank you, and I look forward to talking to you all and seeing
Thank
you all
you.
at OCP Summit. Thank you.
Bye bye.
Bye.
Thank you, everybody. Thank you. Bye-bye.
Thank you.